parametric equations. Many theorems and application in mathematics requires that we have a function y expressed explicitly in terms of x. Graphically, we can tell whether the curve represents a function by using the vertical line test. There are many curves in mathematics that cannot be expressed explicitly using one equation only. For example, a circle, even though the equation of the circle is x squared plus y squared equals r squared, where r is the radius and the center of the circle is at the origin 0, 0, but it is not a function because it doesn't pass the vertical line test. We might express the equation of the circle with y equals the square root of r squared minus x squared, which will give us the upper part of the circle, and the lower part is y equals minus the square root of r squared minus x squared. This circle is expressed using two pieces. This is why it is called the piecewise function. Working with piecewise function can be cumbersome. Not to mention that there are curves where we cannot express y in terms of x explicitly, even if we were to use the piecewise function. Also, in many physical situations, we are not interested in the graph of the function, but we're interested in the motion of the particle. For example, if the particle is moving to the right and to the left, to the right and to the left along the parabola, then having the graph only doesn't describe the motion of the particle. Observe that the position of the particle depends on the third variable, time. So we introduce the third variable t for time, and we notice that the x-coordinate depends on time and the y-coordinate depends on time, where x and y are now functions of t, the third variable. T is called the parameter. The collection of points x, y, where x is defined by a function f of t and y is defined by the function g of t, is called a parametric curve with the parameter t. These equations are called parametric equation for the curve. The set of the value t where these functions are defined is the parameter interval.